Okay, so we're going into chapter 7, and as you can see, this is 7.2. I'm going to make 7.1 an extra credit section. So if you do the homework for that, go ahead and turn it in, and I'll just add, that'll pop up it's about 10 lessons in the homework, so that'll add another 10% to your homework score basically for this one. So you can do that. Plus, don't forget there's a practice test that I'm going to post today, and I'll put that up to be due on Wednesday, and then your test will be due on Friday. We'll give the exam, I should say, on Friday. But I'll put up the practice test. That's also extra credit. Okay, so we're moving into the inference chapters. Chapter 7, we begin statistical inferences, mostly something called confidence intervals, which are basically, we just talk about estimates of things with margins of error. The margins of error come from the probability distribution. And we learn that most of the statistics we're interested in have bell-shaped distributions. So the two statistics primarily are proportions or percentages and means from samples. Both of those, if you do many of them over and over and over again, where you sample from a population and you get either a percentage or a proportion from the sample, and then you plot all the different proportions or sample means that you get, they come out bell-shaped, and there are mathematical proofs for that. And I'm going to kind of show you why percentages and proportions have bell-shaped distributions first, and then probably next week after the exam, I'll show you why means have normal distributions as well. Okay, so this one begins with binomial experiments. We've already studied these. I'm going to stop the share real quick and restart it. Have you guys been able to hear me through all that? Yeah, you were? Okay. The video is lagging, and so it seems like the audio keeps going while the video lags, which is interesting. I'm starting a new share to hopefully take care of that lag. Okay, so we're working on binomial experiments, which are basically an analysis of categorical data. And there's two types of data that we study in this class. There's quantitative data and categorical data. The most simple categorical data is when you only have two categories. And really, you can think of this in any experiment with categorical data where you're focusing on one category, and any observation either falls into that category or it doesn't. And that's binomial. Two outcomes, either it is or it isn't in a category. If it's in the category, we call the outcome a success. If it's not, it's a failure. And so that's a binomial experiment. Okay. Which I'll just review. It has n independent trials. That'll just be a sample. And in every member of the sample, you're just measuring success or failure. P, remember, is the probability of success, and Q is 1 minus P. That's the probability of failure. X is the number of successes. And we've already developed this formula for the probability of X successes. And we just want to practice evaluating the formula once, because that'll come up on your test anyway. Even though this lesson is not on the test, this material was from chapter 5, which is on the test. So let's just practice this. It says, suppose the president has a 45% approval rate, and that you're surveying 10 people, and you're going to ask them how many approvals, and these would be voters, I guess. If X represents the number of approvals, compute the probability distribution below. So you're randomly selecting 10 people, and X is the number of approvals out of 10. You could get any outcome, but some of them are more probable than others. So for instance, let's say you're doing the probability of 4 approvals. That means X is 4. Okay. The formula just says N choose X, P to the X, and Q to the N minus X. Okay. We have to identify N. So N is the number of trials. It looks like there were 10 people. So N is 10. And we gather categorical information. Either they approve or they don't. X is the number of approvals. X in this case is 4. P is the probability of an approval. So P is the probability of a success. Looks like the president has a 45% approval rating. An approval is a success. So little p is 0.45. Okay. Don't forget that Q is always 1 minus P. So that'll be 55% non-approval rate. And one thing about the current president is the approval rate's always at 45%-ish for this guy. And non-approval always about 55% for this guy. That's been true all through the term. All right, but let's go ahead and evaluate the rest of this. So for N choose X, that will be 10, and we're choosing 4 successes and seeing how many ways to do that. Then we're going to do P, which is 0.45. That's to the X, which is 4. And then 1 minus P, which is Q, 0.55 to the 10 minus 4, which will be 6. Okay, so one more thing, 10 choose 4. If I do that on a calculator, I'm going to show you once again how to do that on these little TI calculators. On the TI-36, there's a probability menu, but you got to put the 10 in first. So start off with just a blank screen, put the 10 in. We're doing 10 choose 4. And then up here, you've got a button that says just PRB, I think, for probability. The black calculator has an NCR, and you just have to tap the button till you see it. So this is 10, and that's the choose, and we want to do a 4. So you just put 10 choose 4 like that. And so it's 210. Okay. You can evaluate that by hand, but it's tedious. And I won't go into that now. So 210. And again, 0.45 to the 4th and 0.55 to the 6th because you got 6 failures and 4 successes. All right, so you just multiply this out, and I always type this in one line on the calculator. 210 times 0.45 to the 4th, leave the exponent, times 0.55 to the 6th. Just type it in on one line on your calculator, and it says 0.238 is what I'm going to go with. Well, no, the table has 4 places, so 2383. Rounding to 2384. Okay, so that's the probability of 4 successes. Okay. Now, real quickly, I want to show you how you can do the whole table in one shot on the calculator. Just real quick, I think what I want to do is take that formula again. Probability of X is N choose X, E to the X, Q to the N minus X. The values that we know here, I want to let X vary. So it's 10 choose x, let that vary. P is 0.45, letting x vary here, times Q, which is 0.55 to the n minus x. That'll be 10 minus x, where x is varying, because I want to cover all these values in one shot. The only thing is the calculator is going to want you, I think it's safe to put the 10 choose x in parentheses because it's so weird the way it appears on the screen. I think we should just surround that so that the calculator is not confused. Okay, so that's what I'm going to type in on the calculator, just like that, into a table. Both the TI-30 and the TI-36X, I think will do this. So let me get my camera going here again. Focus. Okay, so I don't use the table very often, but there's a table button on here. Press that. I'm going to edit a formula. So that's item 2 here. And then on the TI-30, it says y equals, on the TI-36X, it says f of x equals just that. Think of that as p of x, okay, probability of x. And start with parenthesis, and it's n choose x. N was 10. The choose is in a button here somewhere, so you got to tap that. Put the NCR up. And then the x is a variable. I'll just tap the variable x button down there and choose x. Those are parentheses. Then it was 0.45 to the x. You won't ever have to do this on an exam, so don't worry about it if you're not following well. And 0.545 to the x, and then times 0.55 to the n minus x. N is 10, so it's 10 minus the variable x. You just type it in like that. That's the binomial probability formula where I put in the values that don't vary, but let x vary. Hit enter. I want the table to start at 0, meaning 0 successes, and I want x to increment in step sizes of 1. So x will be 0, then it will go up by 1 to 1, and then go up by 1 to 2, and so on. It will just automatically generate the table for me, and it does the whole table. Okay, so you can see, I think the handout was asking for where x is 0. That probability will be 0.0025. And you can just scroll through this, and you'll see that the values in the table that are already there are just exactly what this calculator does. And I think I actually used this calculator to make the table on the handout. So I'm just going to pop over now and fill this in. So I think it said that 0 had a probability of 0.0025, so we'll fill that in. Again, you won't have to ever do this again. It's nice for the lecture because I get a lot done quickly. And then I have to scroll all the way down to 7 successes. And my calculator says 0.0746 for that. And then 9 successes is 0.0042 when you round it. Okay. We filled out the table. We're just kind of practicing the binomial distribution. And the binomial distribution, we studied the formulas, we developed formulas for the mean and the standard deviation. So you see those down below. The mean is n times p. So n p, there were 10 trials, and the probability of success was 45%, 0.45. So the mean is 4.5. We'll need that. Standard deviation is square root of NPQ. So this is the square root of 10 times 0.45 and then Q was 0.55. Okay, so all that is under the square root here. So I'm going to put all that in one shot on the calculator. Take the square root button, and then type 10 times 0.45 times 0.55. So it comes out, I'm going to be real precise on this. It's 1.5732. Our goal is to show how the binomial distribution comes out bell-shaped. And then what we're going to do is we're going to show, oh, if it's bell-shaped, we're going to show how you can use the normal distribution to approximate these binomial probabilities in the table. Okay. So I need to do the normal distribution, I need a mean and a standard deviation. So I've got those now. All these formulas, as before, will be provided for your exam. Okay. Any questions? All right, now it's asking on the next page for the probability of a range of values. They're asking the probability that x is between 4 and 6. So I'm just going to grab these numbers. The 4 was 0.2384. We have to add these. So probability of getting a 4 to a 6 is the probability of a 4 plus the probability of a 5 plus the probability of a 6. That's the addition rule. 4 or 5 or 6 is what this means. So again, the probability of getting a 4 is 2384. And the probability of getting 5 up here, you can see is 0.2340. Put that down here. And then the probability of getting a 6 is 0.1596. And the probability of getting 4 through 6 is the probability of getting a 4, 5, or 6, which is the sum of these probabilities. We gotta add them up. Okay, anybody? Let me see if I can see my chat here. 0.632 is what I got also. Thanks, Wendy. Okay, so there's a 63.2% chance that the number of voters that approve of the president will be between 4 and 6. And I did that using the binomial probability formula and the binomial distribution. Now it's asking us to graph the distribution. And you know what I'm gonna do? I'm gonna copy that table so we can all sort of look at it while we're making the graph. So I'm gonna use a little iPad magic here and see if I can crop this table. I'm just gonna take a photo of it and embed it in the lesson further down. Okay, and I want to send that to my document. See if that works. Okay, so somewhere in here, I'm hoping that image appeared. I don't see it. So maybe this isn't working the way my evil plan had planned. Nowhere here. No good. Unless I missed it, but doesn't look like I missed it. So I'm just gonna bring it in again. So plus photo, what did I just take? This one, just one, there it is. Maybe I'll shrink it a bit so it doesn't interfere. Okay, so that's the little probability table. We want to make a graph of that. So I like the idea of doing the middle ones first. Don't ask me why. My highest bar is 0.2384. So I'm going to do that. That's where x is 4. And I usually just do the heights first. So 0.2384, something like that. And then to the right of that is a 0.2340, maybe here. Ugh. 2340. I'm going to try and draw a horizontal line like that. Almost the same height. To the right of that, I have a 0.1596, almost a 0.16. To the right of that, I have 0.0746, which is almost 0.075, which is going to be right about there. Then a 0.0229, just a little more above 0.02, maybe like that. 9 is 0.004, which is about halfway up to 0.01. And the 10 is 0.0003. Pretty much can't see that at all. I'll just do it basically at 0. Yeah. Okay, those will be the heights of my bars. Now I'm going to go to the left of 4, which starts at a 0.1665. Maybe about here. Okay, and then for 2, I get a 0.0763, basically 0.075 here. And then at 1, we get a 0.02, just a little more. Okay. And then at 0 successes, 0.0025, again, it's basically zeroed out at this point. Now this is skewed to the right, but it's bell-shaped. That's kind of the main point here. It's bell-shaped. Slight skewing, not perfect. But it's not bad either. Now remember, the total area under this distribution is 1. Trying to fix something real quick here. Pardon me. I'm a bit of a perfectionist sometimes. And it puts me into these situations where I'm trying too hard. And here I am trying too hard to make this look good. Okay, so I think I'll just do I don't know, I think I'll just do this. I don't know why. No, I think, maybe yes, no, I don't know. Okay, so there's my graph. Remember, the total area is 1. I'd say in terms of shape, it's a bell shape. Oops. Okay. With just minor skewing to the right. So this is less than perfect. Okay. And then it says, okay, if it's bell-shaped, use the normal curve to approximate the probability that we did above. Okay, so the probability we did above was the probability that x was between 4 and 6. So I'm just going to copy that down here. Probability that x is between 4, and this includes the 4, to 6. and use a normal. Crazy. Here goes. I'm superimposing a bell curve here. I'm trying to hit the middles of these bars. As I draw this. It's not easy to do. Really good job, but I'm doing my best. It sort of zeroes out a bit. That rules a few to the right. Now they're asking for the probability of going from 4 to 6. Now remember the rectangles areas are the probabilities. So I'm trying to shade the whole rectangle, not just part of it. And it is the rectangles whose areas are the probabilities. I'm going to use the green curve, which is just not the same as the rectangles. So this method is going to be wrong. But the normal curve is actually easier to work with than the binomial distribution, because the formula, if you're doing large samples, the formula gets to be sort of unbearable. It can be done, but it's not pleasant. Okay, so for the green curve, I'm thinking I'm going to start from the beginning of that shaded region and go all the way out to the end of the shaded region. But can you guys see, this isn't really starting at 4. It starts where? Let me type it in. Ooh, 046. You think that's the wrong answer? 0763. There's a comment that there's a mistake. So let me do that again. So I'm just going to check real quick. So that's the table where x is 70746 is what I got. Let me check the formula and make sure this is correct. Is it good? So Susan, I'm going to pause real quick my recording. Okay, so we've made a minor tweak to the graph, but as far as the numbers on the screen, everything's good here. Now I want to go back. We're trying to find the area under the curve here, but where should I start the region on the normal distribution? Should I start at 4 is the question. I don't think my shading starts at 4. Where does it start? Say it or type it. Look at where my green region. Yeah, that's where the green region starts. It starts at 3.5. And then where does it end? Correct, at 6.5. All right, so when we say x is 4 to 6, that makes sense for a discrete variable. Remember, a discrete variable is one you can count. My share is frozen. This is just a pain about today. Okay, so we're saying x goes from 4 to 6, and that makes sense for a discrete variable. But if you're going to apply a continuous probability distribution, one where x can be any value, not just 3, 4, 5, 6, but the normal curve is a continuous distribution. So we really have to think about how we can correct for a continuous variable. The continuous variable, the bar has to start at 3.5 and go up to the last bar, which ends at 6.5. Okay, so that's a correction for the continuous variable. Don't get too worried. You're never going to do this again after this lesson. Okay, this is just showing you, okay, with a little bit of tweaking, you can make the normal distribution fit the binomial. Okay, that tweaking is called the continuity correction. Okay, and yes, if you want an accurate probability for the normal distribution on a binomial experiment, you've got to do that, right? And yet, don't think you're going to be doing this forever. We only do it on this problem to make this point. And you'll see it in the homework, but then you'll never so it's not like the most important thing you'll do, and it's something you can forget quickly without much damage. So regardless, we're now saying, okay, we're looking at this as a continuous variable. It's a bell-shaped distribution. Let's use the normal distribution, which means we're going to have to change the endpoints on x for this interval. So first x is 3.5, and then x is 6.5. And we'll need to convert to z-scores if we're going to do a normal distribution. So z is always x minus mu over sigma. And this is why we needed the mean and the standard deviation. First x is 3.5. Then x is 6.5. Okay. And then if you go back up and remind yourself, we did the mean, it was 4.5. And the standard deviation is 1.5732. Okay. And now just do the computations real quick. So for the lower limit, I get like a negative 0.64. I'm rounding to the nearest hundredth. And for the upper limit, just change it to a 2. When you do 6.5 minus 4.5, that's 2 over the standard deviation. 1.27 is how I'd round that. Okay, so we're saying that the z-scores would be in this range. So we would change this to the probability that z is between negative 0.64 and 1.27, like that. And then you have to look these up on the normal distribution. So first, we could look up the negative 0.6. and then out to the 0.04. And we'll figure that out in a second. And then after that, we have to do 1.27. So on the other side of the table with the positive z-scores, we'll go down to 1.2 and 0.07. Okay, like that. So let me see here. I'm going to just pop over to, let's see if I can find the table. I have to do it the hard way. Table A1. Okay, and again, reminding myself, we're doing negative 0.64. This one's way down there on the table. Okay, if you can see that, this will be a smaller print this time. Okay, so I'm seeing 0.2611 for that one. Okay, so that's the 0.64. Oh, I forgot what it was already. 2611, is that what I said? Yeah. Okay, now the next one's a 1.27. And that'll be on the other side. So 1.2 and then all the way up to 0.07. Okay, so that's the other endpoint, so 0.8980. Okay. 8980 it said. Okay, and we want z to be in between these, so you take the bigger area and you subtract the smaller. So it's 0.8980 minus 0.2611. Any chatter on that point? Yeah, 6369. Let's round that to 0.637. Well, that's okay. 6369. That's fine. Okay. So 63.69%. What did we get up above? 63.2%. So here, 63.2% is what we said the probability was of getting between 4 and 6 approvals. So 63%. This one's 63.6% or 63.7%. So about 63% either way. And this is with a normal approximation where I said there was minor skewing. So it's not really a perfect bell curve because of that skewing. 63.7 is really close to the correct value of 63.2. Okay, so I would just make the comment that the normal distribution makes a good approximation for binomial probabilities. And I'm going to put a little caveat in here and say if they are not too skewed. left or right. Okay, so that's the trick, is we need to know, we're going to be using the normal distribution exclusively for binomial experiments. You don't have to. You can use the binomial probability distribution, but it's really hard, and it would be super hard without a computer, because there's just, the binomial distribution is just a lot harder to work with when the numbers get big. Okay, and so the normal is just easier. And so the question is, what can we do to know that the normal distribution is going to work okay? Because if the binomial distribution is very skewed, then I don't think we can use it. Okay, so we're going to have to come up with some rule for when the binomial distribution is not skewed. We need it to be symmetric. Okay. So I want to move on for that, and that's what we're going to work on now. We're going to use a computer simulation to see if we can come up with rules for when the normal distribution will be a good model for the binomial when the binomial is not too skewed. Okay? So that's what we're going to do next. I'm going to pause my recording. Okay, so this, as I said, this applet shows an entire binomial distribution. It'll give individual probabilities. And just let you guys know, all I did was I just Googled binomial distribution applet. And so this is the first one I saw, and it's pretty good. I'd like to go ahead, we just did 10, where the probability of success was 0.45. And I think if you just put in those parameters, you get the whole distribution. And if you're interested in particular probabilities, you just use your mouse to hover over it. And these are the probabilities we were just working with. So I think the probability of 2 was the 0.0763. That number should sound familiar because we were fussed about the height of the bar that I drew for that one. But so anyway, just computes all the probabilities. Looks real nice. You can, and as in the picture we drew, it is bell-shaped, but you can see that slight skewing. I think this will work better if we do our sample size a little larger. So I'm going to go up to 100 here, and you can see that's a great bell-shaped distribution, and I don't see any skewing at all. So it seems like it's reasonable to think that by increasing the sample size, we can make this look bell-shaped. Let me go back to a sample size 10 here, and I want to show you a case where it's horribly skewed. So let's go to a 0.2 for P. So that's very much skewed to the right. And it just has to do with the fact that the mean, remember the mean is n times p, and you can see down here the mean. Okay, the mean is n times p, so 10 times 0.2 is 2. If the mean is 2, then you're not going to have room on the left for a left tail. There's plenty of room on the right. Okay, so the mean can't be too close to 0. Also, the mean can't be too close to whatever the number of trials is. This one has 10 trials. If p is 0.8, then the mean is n times p, which is 8, as you can see down below. So now the mean is too close to the right-hand side, which is n, the number of trials. Here it's 10. And it's skewed to the left. Plenty of room on the left now, but there's no room on the right. So again, this is not normal looking. But again, what can we do about that? Well, you have complete control over your sample size in statistics. So if you pop it up to 100 for the sample size, then you get this beautiful bell-shaped distribution. So by increasing the sample size, you can make the distribution of probabilities bell-shaped. You just have to get it up big enough. And basically the rule is going to be that, that the right tail, and let me go up to a 0.9 for P so you can see. So right now, notice that the mean is 90. Okay, you can see it down here. The mean is 90, and with a mean of 90, there's a distance of 10 on the right, because this distribution only goes up to 100 successes. Okay, so on the right, from 90, there are 10 more bars. Okay? And generally the point of view is that it's enough as long as there's 10 bars on the right, and that's generally enough to get them to zero out. Okay? And like the normal distribution does, it zeroes out. And of course, there'll be plenty of room on the left for that to happen. So basically, from the mean, we need the tail on the right of the mean to be at least 10 in length. Okay, if I do like a 0.95 now you can see the mean is 95, which is n times p, 95. And now this is just looking a little too skewed. With a mean of 95, the tail on the right only has a length of 5. And a length of 5 is not enough for that last probability to zero out properly. So we'd say this one doesn't look bell-shaped because it doesn't zero out on both sides, therefore it can't be symmetric. Okay, same thing on the left. If p is 0.05, then the mean is now n times p. 100 times 0.05 is 5. So the mean is 5, and there are 5 bars on the left of 5. So it doesn't zero out. It's not enough. Okay? If p was 0.1, still looks a little skewed to me, but the mean is 10 now. And with 10 bars to the left, it does zero out. And that's sort of our rule. It needs to zero out before we'll say, okay, it's got some chance of being sort of symmetric. And so we just say that as long as there's 10 bars to the left and 10 bars to the right of the mean before it zeroes out, and it must zero out on both sides, then we'll say that's going to be close enough to symmetric to use a normal distribution to approximate it. Again, if p is 0.05, then that's just only 5 bars on the left. The mean is now 5. Okay? And there's only 5 bars to the left of the mean. And we're going to just say that's just too skewed. We can't use that. But the solution of too much skewing is always to, and you can't control the population proportion. If it's 0.05, it's 0.05. Nothing you can do about that. But you can increase your sample size. So if you go to 1,000 in your sample, then even with a 0.05p, the mean is now 1,000 times 0.05, which is 50, which means there's 50 bars to the left of the mean. And that's plenty of space to form a nice tail on the left and on the right, and it looks bell-shaped and just so symmetric. So these binomial distributions can always be made to look bell-shaped if you can just pump up your sample size large enough. And we just say pump it up large enough so that the number of bars on the left is at least 10, and the number of bars on the right is at least 10, and then we'll say that's roughly a normal distribution. Okay, so let's do, the question is the normal distribution, oh, hang on, I don't know if you're seeing this. Something went wrong. There we go. So the first question is, it says the computer's, or the instructor's done the simulation. When is a binomial distribution approximately normal? Is the normal distribution always a good approximation? The answer is no. Sometimes the binomial distribution is skewed. Okay, so let me just do a little kind of a picture here that'll kind of tell the story we want to tell. So I'm just going to do a bunch of bars here. And nothing like precise. Okay, my last bar I'll do over here. Oops. Okay, so something like that. I'm going to add some bars on the other side. Okay, so somewhere in here, you're going to have the very first bar, and that's where where x is 0. I'll just put a little 0 there for x. And the bars just go on and on and on. Eventually, you get to a last bar, and that's where x is the number of trials, so that's m. There were n trials, so the most number of successes you can have is m. Okay, and this is a number line for x here. Now the mean is the highest bar usually, so that's going to be mu, which is np. Right? And the left tail and the right tail are the distances we're focusing on right now. Right? The left tail's area, or sorry, length, is just the distance from the mean to 0. And of course, that is the mean, which is np. Okay? The right tail has a length of, well, just take the big number and subtract the small number. So it's n minus np. A little bit of math says that if you factor out the n, is n times 1 minus p. And a little bit more math says that that's n times what? That's 1 minus p. Just to see if you're paying attention. Right, thanks, Wendy. It's nq. Okay. And I said that these are the lengths of the two tails. NP is the left tail, NQ is the right tail. Statisticians have decided that that needs to be at least 10 on both tails. NP, at least 10, the average number of successes. NQ, at least 10, the average number of failures. Okay, so the rule, which I'll call the criteria, the rules, the criteria for normality, very simply, that NP has to be at least 10. That's the length of the left tail. And NQ has to be at least 10, and that's the length of the right tail. Okay. I'm going to give you guys a second to ask questions. I want to try and punch out the rest of this lesson. I'm not going to get all the way through. But let's see what we can get done here. All right, suppose you actually conducted the experiment and observed 6 approvals in a sample of size 10. The proportion is going to be called P with a hat. This is a sample proportion. Okay. The sample proportion is 6 out of 10, which is 0.60 or 60%. Okay. What's the probability of getting a 60%? Well, the probability that P hat, the sample proportion, is 0.60 is the same as the probability that X is 6 out of 10. So the probability of getting a 6 was back here. We can use this table. I'm just going to copy this, I think. There we go. And maybe paste it down here. Okay, so the probability of getting a 6 is 0.1956. And if you've gotten 6 approvals out of 10, that's 60%. So it's the same as the probability that the proportion from your sample is 0.60. So those are the same thing. So we've already done that. And so what we're saying is that these sample proportions have the same probabilities as the probabilities from the binomial experiment. Again, p hat, this is sample proportion. Okay. And the probabilities for the sample proportions are the same as for the binomial experiment. So if we have x equal to 0, x equal to 1 out of 10 is 0.10. X equal 2, that's 0.20 for 2 out of 10. And as so on. Okay. And the probabilities are the same. Okay. So for 0, that's right. For 0 successes, that's a proportion of 0 again. Okay, for 1 success, that's 10%. For 2 successes, that's 20%. And so on. So we just fill in the same probabilities, 0.0025, 0.0207 is there, 0.0763. For 40%, that's the same as getting 4 out of 10, which is 0.2384. 60% was 0.1596, 6 out of 10. 70% is 7 out of 10, 0.0746. And 0.9 is a 0.0042. Okay. And, you know, I could copy this. Let me see, we have to graph this. So how are we doing for time? Got 6 minutes. Let's do our best. So now I'm trying to do a picture real quick that I can copy. I'm a little trouble. Oops. That is not what I meant to do. Okay, pardon me while I get that back. I'm having all kinds of trouble right now. That's working now all of a sudden. Okay. Now these are the same probabilities that we worked with before. So really you're drawing the same histogram here for the proportions. And so you're gonna hate me. You probably already do, except for I've made a mess. I don't care. These are the same probabilities. So why not use the same graph? I'll delete the mess inside. I think it's safe to say if a binomial distribution is normal, these aren't going to, the scaling on this is going to be a little off, so don't hold me to be too precise on this graph. Okay, I'm just trying to save time. Okay, it's the same probabilities. So if the binomial experiment is normal, then the sample proportions are going to be normal as well. So the distribution of sample proportions is approximately normal. Now that's only going to be normal if the binomial distribution is normal. Now I'm going to give the provision on this. We said that the binomial distribution will be approximately normal, provided NP is at least 10. Remember, that's the length of the left tail. And NQ is at least 10, which is the length of the right tail. We want the tails to be long enough. Now that technically is not satisfied here, but it still looks pretty bell-shaped. All right, we're out of time. I think this is actually a pretty good, well, we have to figure out the mean and the standard deviation, but for the moment, I think let's just call it a day right there. I'll be posting, so we have not finished 6.2. Don't worry about any homework for it right now. You could probably do most of it if you felt like it, but I'm not going to collect that next week. So I'm just going to collect homework for chapters 5 and 6, and that's what the test will cover. Yes, there are office hours at 11:45, so I'll take a short break, and then the office hours are in a different Zoom meeting. So if you go back to Canvas, you'll see a link in the announcements and also on the schedule, and the password's the same. It's MSAC. From Outsac, just MSAC. And again, the link is in Canvas, and I think I emailed you the link last night as well. So in multiple places, you'll see that link in Canvas for this class. So I'm gonna go ahead and take a short break. If you guys need to talk to me, Johnny, we're gonna put ice on the projects, you guys. I just think as it stands right now, there's just too many difficulties right now. So don't worry about projects. I know there was one person anyway that was looking forward to doing it. And I think the way things stand, it's just too much. So let's just forget about it. Things change in a pandemic. So like I said, give me 5 minutes and I'll see you guys at office hour. Any of you guys that want to talk to me, it will be at the other Zoom link. So I'm going to stop this Zoom meeting and I will see you guys over there if you need to talk to me. Okay, so the sample proportions, I say, are normally distributed. The mean of sample proportions is the mean of the binomial experiment divided by the sample size, so you get 0.45, and 0.45 just happens to be the population proportion. Okay, if you do the same thing with this standard deviation, this standard deviation is the standard deviation from the binomial experiment. This standard deviation is the standard deviation of sample proportions. Because we divided by 10 to make the sample proportions, the standard deviation gets divided by 10, and you get a new standard deviation for all sample proportions. Here's the formula. It's just me developing the formula, the standard deviation of all sample proportions. And let's go ahead and kind of summarize all of this using a central limit theorem, which just says that our statistic has a normal distribution under certain conditions. So here comes sample proportions. From samples of size n. Drawn from a population. Oops. With proportion p are normally are, let's say, approximately normal in distribution. Provided what we said before is that the left tail and the right tails of the binomial experiment have to be at least 10 in length. Left tail is NP, that has to be at least 10. And the right tail is NQ, which also has to be at least 10 in length. Okay, that's just the distance from the center to each, the end on the left and the right of the distribution. Those are what I'm calling the tails. Okay. Also, the mean and standard deviation which in future I'm going to call standard error, and I'll explain why. So I'll say to be called standard error. Are mean of sample proportions and standard deviation of sample proportions. Where the mean of sample proportions is the population proportion, and the standard error of sample proportions is a little more complicated. It's the square root of PQ over N. Okay, so this is again the mean of all sample proportions. And the sample proportions are p hat, remember? Okay, and sigma p hat, that's the standard error. Of all sample proportions. Okay. We call it a standard error because you're taking the standard deviation of a statistic. P hat is a sample proportion. It's used to estimate a population proportion. Standard deviation, you're measuring the average deviation from the mean, which is the population proportion. And when a sample proportion deviates from the population proportion, that's just an error. Again, you're estimating the population proportion. So deviations in estimates are errors. And so we stop calling this a standard deviation and start calling it a standard error when it's the context of an estimate of some value. Okay. Any questions? Okay, and talking about estimates and errors, we're going to go ahead and see if we can come up with a margin for error in a sample proportion. So here's the idea. The mean of sample proportions, and I think what I'm going to do is make this a distribution of sample proportions here. And just say p-hat values are approximately normal. If you're basically your sample size has to be big enough so that NP is at least 10 and NQ is at least 10. Okay. And normally what we want to do is, first of all, know the mean and the standard deviation or standard error of our statistic. The mean of sample proportions turns out, oops, this should have a p-hat down here. So the mean of sample proportions is the population proportion. Okay. And the empirical rule says that 95% of that, because it's bell-shaped, 95, so if I put a 0.95, I think I may erase this here. It says that 95% of the sample proportions will be within 2 standard deviations, 2 standard errors, okay? So if I go up to the population proportion plus 2 standard errors, so the standard error was sigma with a little p-hat here. And if I go from the population proportion minus 2 standard errors, oops. So this is just a range of 2 standards. Again, I'm going to erase all that because it's the 2 standard errors is not as precise as I want it to be. So if I go up 2 standard errors and down 2 standard errors, I'll capture 95% of that distribution. And that means that 95% of the time, my p-hat value will be in that range. Okay, so if I've chosen a p-hat from a sample, 95% of the time, it's going to be within 2 standard deviations of the population proportion. That's what that says. And so let's use 2 standard deviations as the maximum error. You don't know the error in your statistic because the population proportion, this thing right here, will be unknown. Because you don't know the population proportion, you can't know your error. But we know that 95% of the time, your sample proportion will be within 2 standard errors of the population proportion. And this picture kind of tells it all. Okay, hopefully that makes sense. So we just need to do 2 standard errors. That's good 95% of the time. But the problem is that sometimes people want to be right more than 95% of the time. Okay, what if they wanted to be right 99% of the time? Then that sort of changes everything. Okay, so I'm going to add something else that I'm going to also erase, but for the moment I'm going to put a 0.99 in. That's the area of, so that's the area of this white region, which is also called the level of confidence. So because I want to be right 99% of the time, I'll be 99% confident in whatever I say. Okay, so if I want to be right 99% of the time, that's going to kind of push out my margin of errors because I need to take up 99% of the curve now. Okay, so I'm not going to be able to go up 2 standard errors anymore. So how many standard errors is the question? Let's go to the normal distribution and draw, sorry, to the standard normal. Notice these are z-scores down here. That's called the standard normal distribution that's centered at 0. Okay, so let's do it there first and then we'll bring it back. I need to know how many standard errors, and so this right here is going to be the number of standard errors. Remember, standard error is just another word for standard deviation right now. So the number of standard errors in the margin for error and the margin for error is going to be called E. And the number of standard errors is just going to depend on how confident you want to be in your statistic. Okay, so if you set this up, you want to be 99% confident here, you got to figure this z-score, which is called z alpha over 2. Now let me explain the alpha over 2 part. Okay, so we define alpha to be 1 minus the level of confidence. Okay, so that's going to be these two tails. Remember, this is a rule of complements thing. If you're doing 99% for your level of confidence, then 1 minus the level of confidence is the two tails combined. So each tail would be alpha over 2. Okay, does that make sense? So if you're doing 99% confidence, then alpha would be 1 minus 0.99. So this is going to be 0.01, and then the alpha over 2 would be 0.005, which is half of 0.01. Okay, and then we're pretty good. If you know, and this is going to be on your exam, if you know the area of the right tail, you should be able to find this z-score. Okay, and so we'll talk about that, you know, the actual logistics of doing that in a little bit. But right now, we just want to go ahead and say, hey, we're going to be able to find this z-score. Okay, and once you know the z-score, that's the number of standard errors in the margin for error. And so when I come back to this picture here, I'm not going to do 2 standard errors if I want to be more confident. Okay, I'm going to do this number, z sub alpha over 2, and it's called that because you're kind of cutting off a tail whose area is alpha over 2. So whenever we have a special value of a variable, we often put subscripts on it like that. So you're not multiplying z by alpha over 2. It's just a notation that it's a special z-score. Okay, and that's the number of standard errors in the margin for error. So if I go back to this formula here, instead of going up 2 standard errors, I need to doctor this a little bit. I said I was going to change this, so I hope you were listening. Instead of 2 standard errors, I'm going to go z alpha over 2 times the standard error. Okay, I'm going to move that just a bit. Instead of 2 standard errors, I'm allowing this to vary. I don't know how many standard errors. It depends on my level of confidence. Okay, and instead of 2 standard errors on the low end, I'm going to do z alpha over 2 standard errors. Okay. And if I go z alpha over 2 standard errors to the right of the or the left, of the population proportion, which is the mean, then if I'm using 99% confidence, then 99% of sample proportions will be contained in this interval. Okay, so I'll just go ahead and say 99% of sample proportions, because it's a bell-shaped distribution. I'll just use the bell curve to find that z-score. 99% of sample proportions are contained in this interval. Okay, so the true error is, and I'm not going to be able to denote this. I'll draw an arrow to it. So the distance between that sample proportion and the population proportion is the true error. And I hope you can see that true error is less than the number of standard errors that makes the width of this interval. Okay. The true error should be less let me fix this. And I'll put it in absolute values. Okay, the true error should be less than z alpha over 2 standard errors. For 99% of sample proportions. So I'm only 99% confident, and that just means 1% of the time I'm going to get one of the sample proportions that lives out in this tail. Okay, so if I get a, if I get a p hat value right there on my number line, that thing is extreme. It's out in a tail. It's unusually high, and it's something like that. If you're doing 99% confidence, then getting something this high, that should only happen 1% of the time. Okay, 1% of the time you're going to get a sample proportion that's outside of the interval. Okay, and remember this interval, I don't know where to denote this. I'm going to squeeze it in somehow. That's not good. Okay, this interval, right, this width right here is the number of standard errors. So that's our z alpha over 2 times the sigma p hat. Okay. So we're going to just call that thing the margin of error. So this is going to be big E for the margin of error. It's not the error. It's the margin for error. It's how much error we're allowing ourselves and saying, I think whatever my error is, it should be less than this. And I'm only going to be right 99% of the time, because 1% of the time we know this is bell-shaped. If it's bell-shaped, then we know all the stuff we need to know about the distribution, and we know that 1% of these values is going to go outside the interval. Okay? And for those values, the true error will be bigger than the margin of error. It just will happen. So let me finish what I was writing down here. For 99% of sample proportions, okay, so let's just go ahead and put the margin for error in. little caption down here. E is this Z alpha over 2 value times the standard error, which was sigma p hat. But just this once, I'd like to put in the formula for sigma p hat, which means I don't have enough space. Typical. Let's see, I'm just going to move things around a little bit here. Okay, so my margin for error is this z-score, which is just the number of standard errors that'll capture 99% of my distribution. So I got to figure out, well, what's the number of standard errors? And just count that many standard errors. And the standard error, when you look at the formula, is the square root of PQ over N. Okay, and that's what's done up above back here. Okay. All right, so that's maybe a bewildering development. So what I need to do is do some examples. And so we'll do that next. Just gonna pause and see if I have any questions. If you have a question, then go ahead and pipe up, send me a chat. Or just unmute yourself. So Jonathan, I'm recording this and you can go back. I don't know what you missed. I talk pretty slow, so. Anyway, so I want to go on back and start with section 7.3. This is called confidence intervals for a population proportion. And this is nothing more than looking at a sample proportion, which is p hat, hoping it's one of the proportions that's inside the interval. So if you're trying to capture, if you want to be right 99% of the time, then you're going to give this interval. Forgive me while I try and fix this. Okay, so you're trying to highlight an interval that I've just drawn in red. 99% of the time, your sample proportion will be within that interval. And therefore, whatever margin of error you give will be correct. And that's all we're doing. We're just giving a statistic and determining the margin of error. The margin of error is using z-scores from the normal distribution. And there's a requirement for normality that n times p and n times q have to be at least 10. So that's something you have to check on all of these problems.